Alright, in this section we're going to talk about determinants and Cramer's rule. We're going to talk about how to evaluate determinants, use Cramer's rule to solve linear systems, and then evaluate determinants. So the determinant of a 2 by 2 matrix is written A, and its vertical lines looks like an absolute value mark, but it's not when it's a matrix. That means the determinant of the matrix. And it's A11. Now what that means is that A is in row 1, column 1. A22 is in row 2, column 2. So in other words, I'm going to multiply on this diagonal, then you're going to subtract, and then you're going to multiply on this diagonal, like that. And sometimes this is written, if you have matrix, and it's A, B, C, D, like this. And so A, the determinant, is A, D minus B, C. And so that might be a little easier to see what you have to do than using all the subscripts. Okay. Alright, so evaluate each of these determinants. For A, you're going to have negative 2 times 3 minus negative 1 times 3, which is negative 6, plus 3, or negative 3. For B, you're going to have 2 times 6 minus, parentheses, negative 4 times negative 3, or 12 minus 12, which is 0. It is, the determinants can have a value of 0. But when we're using Cramer's rule, which we'll talk about in a little bit, one of the determinants cannot be 0 and use Cramer's rule. But it is a legitimate thing to come out with 0 as a value of a determinant, at least on occasion. Alright, so we also, when we have larger matrices, we have minors and cofactors. Minors, the minor of a 3 by 3 matrix is a 2 by 2 matrix. And we'll cross out the row and the column that that element is in, and what's left uncrossed out will be the minor. The cofactor is negative 1 raised to the I plus j power times the minor. Okay, so let's talk about this a little bit. Evaluate the minor of A12. Well, A12 is row 1, column 2. So this is the minor. I mean, that 3, that value of 3 is A12. So we're going to cross out row 1 and column 2. And so the minor is going to be 1, negative 1, negative 3, and 0. That's going to be the minor of A12. And so then the determinant of that would be 1 times 0 minus negative 3 times negative 1, which is 0 minus 3, or negative 3. Okay, so that would be the value of that minor. Now, the cofactors. I want to talk about cofactors a little bit. Cofactor of A to the 2 plus 3. Let's get rid of this that I've written so far. Okay, erase it. Okay. Alright, so now we've got a cofactor of 2, 3. Well, cofactor is the negative 1 to the 2 plus 3 times the minor, okay, and row 2, column 3 is here. We mark out row 2 and column 3. So the minor would be negative 5, 3, negative 3, 1. And so negative 1 to an odd power is going to be negative 1, or negative. Then we'll have negative 5 times 1, which is negative 5, minus negative 3 times 3. So that's negative 5 plus 9, or negative 4. I mean positive 4. Should be the... I'll get that right in a minute. Never mind. It is negative 4. Because this is positive 4 and the negative in front makes it negative. Now I want to talk a little bit about this value right here. We can, if you just get in mind this matrix, you can do this each time, but also if you notice, one way to do the cofactors is if you start with positive here and then alternate signs. If you notice, 2, 3 is in this spot right here, row 2, column 3, and it's a negative. It changes the sign to negative, which is what this did right here, because negative 1 to the 5th power is negative. That's where that comes from. So you can just kind of realize that those cofactors go like that, positive, negative, positive, and then you don't have to multiply them every time. That's up to you. You can use the formula, or you can use my little cofactor sign chart. Alright, so let's look at what they have to say. They've shown crossed out row 1, and this is for A12, row 1 in column 2. The pink will be the minor, and we've got a value of negative 3, which we did. Now B, we have the cofactor, which we got, and it came out to be negative 4. So they agreed with us, and that's a good thing. So let's move on. Evaluation of an n by n matrix determinant is accomplished by expansion along a fixed row or column. And it doesn't matter what row or column you use. So that's important. Usually what you want to do is pick a row or column, decide to use the first row or decide to use the first column. It's just easier that way. So we've got this determinant of an n by n matrix. We've got, they're using the first column. So they're going to have whatever number is in A11 multiplied by its minor. And then remember, the sign changes for the second one. So it's going to be minus A21 times its minor plus A31 times its minor. Okay, so let's just do it and see. So again, we're going to decide which column or row we want to expand along. They say use a column with many zeros. I honestly prefer just using a column that's the same as I always use the same one. I always use the first row or the first column. They're going to use row 2 because it has the most zeros. So they're going to expand along row 2. So you're going to start with negative 2 times its minor. So to get its minor then, to find the minor of row 2, remember we're going to cross out row 2 and then the column that it's in. So its minor is 3215. You can see that. Okay. Then I'm going to cross out the second column for the second minor. So I get negative 1, 2, 4, 5. And then the third column for the third minor, which is negative 1, 3, 4, 1. So that's how you're going to get those minors. And remember, this is going to be positive, this will be negative, and this will be positive, or positive, negative, and positive. So, since 0 is neither positive or negative, they didn't really switch the signs on that one. Since it's the middle row, it starts negative. So we have negative, negative 2. Remember, we have negative, then positive, then negative in the middle row. So, that's why those signs here and here are what they are. Okay? So then you evaluate your minors. 15 minus 2 is 13. 0 times anything is 0, which is one reason to use the row with the zeros. And so the value is 26 of this determinant of this large 3 by 3 matrix. Okay? So the determinant of A, and what you're not seeing there are the two vertical bars. The determinant of A equals 26. You can get the same answer if you use a different row or a column. Doesn't matter. They're going to use this column. Again, though, it's going to be positive, negative, positive for the sign changes. And so just to see, there's the minor 0015. Okay. Then for the second minor, it would be this 3215. And for the third minor, it would be, cross out the last row, so it would be 3200. So you have -1 times 0, which is going to be 0. And then +2 times 15 minus 2, and then 4 times 0, and so you still end up with 26. And so the absolute value of A is 26, no matter how you do it. Okay, properties of a determinants. You can factor out a constant. So I could say that the first minor is equivalent to 5 times 2 negative 1, 3, 1. And 4, 7, 12, 9 is the same as 4. And you divide the first column by 1, 7, 3, 9. Personally, I wouldn't do this. I would just multiply them. It's not that hard, and you have a calculator. So I don't see any reason really to factor out terms like that. I think it just makes it more confusing. Okay, you can interchange 2 rows or 2 columns. You can see that they've swapped rows in the first 2 matrices. But when you do that, you have to multiply by -1. And they changed 2 columns in the second one. Swapped them, but they multiplied by -1. Again, why? Because it's just going to make things complicated. Okay. A determinant is unchanged by adding a multiple of one row or column to another row of column. So if I have 3 times R2 plus R1, and you make a new row 1, then that's fine. You can do that. So here we've got a 4 by 4 matrix, so it's very large. So we're going to use the properties of determinants to try to obtain rows or columns with as many zeros as possible. Okay. So -3 times row 3 plus row 2 makes the fourth column have only one non-zero entry. Okay. So now we're going to expand along the fourth column because it's only got the one non-zero entry. Okay. So you've got this. This is your matrix, or this is what you're going to find the determinant of. So -1 and again, if we start with it's column, it's row 3, column 3. So this 1 that we're working with here is in position 3, 3. So that adds up to be 3 times 3 is 9. So you remember the part of the cofactor. The reason this is negative is because it's -1 to the 9th power, which is negative. So that's why we know everything else is going to be a 0 except that one. So we have -1 times this minor that we get by marking out this and this. Okay. So far so good on that one. Okay, so we're going to go through then, and we're going to swap column 1 and column 2. Now we're going to add column 1 plus column 2. Add the first column to the second column. And replace the second column. And what that does is that gives us another 0 in that third row. Okay. Then we're going to expand along the third row. So we have negative 2, and that 2 comes from here because we're expanding along the third row, so that's where that 2 comes from. And the minor for that, when we mark out the row and column the 2 is in, is 2, 3, negative 6, 4. And so we have negative 2 times the determinant of what we see there, which is negative 8 plus negative 8 minus negative 18. So that becomes negative 8 plus 18, or 10. So the determinant will be negative 20. Okay. So that is, I guess, why you would do that. I am not going to ask you to do any large matrices like that. But that is how you would do a larger matrices. Whoops, sorry. Okay, so we've reduced the work from a 4x4 matrix to a 3x3 matrix, and then we got down to a 2x2 matrix by doing those row operations. Okay, Kramer's rule for a 2-variable, 2-equation linear system. Okay, so this is, again, Kramer's rule. You have to, when you have a 2-variable system, you have to get 3 matrices. You get one for the x variable, one for the y, or 3 determinants. One for the x variable, one for the y variable, and then what I call a coefficient determinant, which is your denominator. That's the one with just a d. That's the one that cannot be 0 to use Kramer's rule. You can have a 0 in the numerator, but you can't in the denominator. So that D matrix, or the coefficient matrix, cannot be 0 to use Kramer's rule. It has a value of 0. It's just that we can't then use Kramer's rule to solve these systems of equations. Okay, so let's just look at what we've got. So we've got this system of equations. We've got kind of coefficients 4 and negative 3 in front of our x's, negative 5 and 7 in front of our y's, and 3 and 1 are our constants that are after the equal sign. For dx, we replace the x column with the answers. For dy, we replace the y column with the answers. And for d, we just use the coefficients in front of the x and y. So notice here that we're doing d first. So we're using the x, 4, negative 3, and the y, negative 5, 7. And you get the determinant. Okay? Then you have to find dx. Okay? Calculate d first, because if d is equal to 0, you can't use Kramer's rule. So, in other words, we do that, we find out that it's not equal to 0, so we can use it. Now for dx, we replace the 4 and negative 3 with the answers, or the constants 3, 1, and get the determinant in the regular fashion. 21 minus negative 5 is 26. Now we can calculate x. X is dx over d. We can get dy. Again, you replace the y column with 3, 1. Okay. Now dx over d is 26 over 13, so x is 2. dy over d is 13 over 13, so y is 1, and solution is 2, 1. So we found our solution to our matrix. For b, when we calculate d, we find that it's 0. So since d equals 0, there is not a single solution. It's either going to have no solution or an infinite number of solutions. So if you replace the negative, do the same thing with dx as we did before, find out that's 0, and dy, we find out that that is also 0, then the system is dependent. They're all equal 0. That means the two equations are multiples of one another, and so the system is a dependent system. Okay. Now, a linear system of n equations in the n variables x1, x2, however much to xn can be written in this form. Okay. Solution x is dx over d. The second one is dx over d all the way to dxn over d, where the determinant of the coefficient matrix in D is the determinant of the same matrix with the ith column. So in other words, we're doing the same thing, it's just bigger matrices. So this one is a 3-variable system where there's no x there in the second equation. You're going to have to put a 0. So we're going to look at, we have to expand. First we put our d, we're going to solve our d. And again, remember you put a 0 if there's not an x, you have to put a 0 there. We're going to expand along the row or column. Doesn't matter which one, you can choose. In this case, they're doing row operations. Personally, I wouldn't do that. I'm just going to go and do it, show you what I would do. I would expand usually along this first column here. I would expand along this first column. And so I'd start with, remember, it's plus, minus, and plus. So I would use 3 times the minor, which if I mark out that row and column is going to be 3, 1, 1, 2. Then it's minus 0 times the second minor, which if I erase this, then it's this one. So negative 2, 1, 2. Okay. Plus, and then we've got